7.1 starts off with a description of what is a continuous random variable. So a continuous random variable is going to be a situation, like an experiment, where the resulting variables have an infinite number of possible outcomes. Because they have an infinite number of possible outcomes, you can't list them all. That's different from chapter 6, where we had a discrete random variables, where you can write them all, right? So when we looked at binomials, you had 0, 1, 2, 3, 4. Well, here there's just an infinite number of possible outcomes. You can't write them all. So we have to describe them by writing down either the entire number line from positive infinity to negative infinity, or some segment of the number line where every number between those two values is equally likely of occurring. Okay? All right, so now the key to this is that the picture above the horizontal axis describes for you the likelihood of a value occurring. So they, for example, might have a shape that kind of looks like this. Say something like this, where this is maybe centered around 7 and this is centered around 11. Right? What this picture is indicating for us is that although any number is possible from negative infinity to positive infinity, some numbers are more likely of occurring, and the values centered around 7 are more likely of occurring, and the numbers centered around 11 are more likely of occurring. Is it possible that I randomly pick a number and the number is 23? It's possible, but a lot less likely than a value over here, right? That's what that picture above is describing for us. Now, we're only going to be dealing with a couple of distributions in this class. One of them is uniform, which we talked about before, and then what I want to focus on now, which is normal distributions. So in a normal distribution, let's say we have that. Normal distribution will look something like that. It's bell-shaped. That's one of the characteristics of a normal distribution. So you can use those words synonymously, a bell-shaped distribution or a normal distribution. Normal distributions are symmetric. It's very important. That means that if we cut them in half, the left-hand side is equal to the right-hand side, right? So they're symmetric. They are centered at the mean. The mean and the median are both the same. We use mu to indicate the mean of a population. And they have a certain standard deviation, sigma. The value of sigma, the standard deviation, is a value that attempts to describe the spread of the data, right? So when sigma is big, the data is really spread out, and when sigma is small, the data is really compact together, right? Okay, so we label this as a normal distribution. Okay, so we know that. We also know from the empirical rule back in chapter 3 that within one standard deviation of the mean, we find about 68% of the data, and within 2 standard deviations, we find about 95% of the data, and within 3 standard deviations, we find about 99.7% of the data. Okay, so that's kind of useful when we want to do like a rule of thumb guideline, but in this chapter, we want to get more precise. Okay, so the other really important characteristic about normal distributions is that the area underneath the curve from one normal distribution to another normal distribution is proportionally equivalent as multiples of standard deviations. So I'll show you what that means in more detail in one second. Another important characteristic about normal distributions is that this line here goes on forever. It gets infinitely close to the horizontal axis, but never actually equals it, never actually goes below. So no matter how far away we are from there will always be a little bit of a gap, a little bit of space between that curve and the horizontal axis. Good. All right. So now, if this is a shape which describes the likelihood of the values along the horizontal axis, let's use x to be the variable in this case. If in fact it describes the probability of getting certain values, then certain characteristics have to be true about the distribution. One is that the sum of the area underneath this curve has got to be equal to the whole area has to be equal to 1, 100%, right? You can't have it be equal to anything else. It describes the likelihood of any value on the horizontal axis, so the whole area has got to be equal to 1. That's a very important characteristic. And none of the probabilities are allowed to be negative, so you can't have this curve go below the x-axis either. Okay, so here's an example of a normal distribution. Maybe here's another example. Maybe this one kind of goes like this and goes this way. Maybe another one will go up really tall and come back down. Maybe another one will kind of go like this. Right? So they're all different iterations of a normal distribution. So they're all normal. Normal. Normal, and normal. So what's different about them? Well, they're centered at different places along the x-axis. So like, I'm just making numbers up here. Let's say this one is centered at 3, and it's got a sigma value of, I don't know, say sigma value of, well, it's a little short. Let's say 4. Just making the value there up. Okay, so then this one would be someplace else along the horizontal axis. So maybe it's the mean value of, I don't know, how about 7? And then a sigma value of, okay, well, if this one is a 4, what kind of sigma value could this one be? Because it's skinnier and taller, it indicates that the standard deviation is smaller or bigger. It's got to be smaller, right? It's more compact. It's more likely of occurring that a number occurs is going to be centered around 7. So this one might have a sigma value, and again, I'm just making stuff up of say like 0.5. Whereas say this one has a mean of like 11, it's centered at 11, and it's got a sigma value of, okay, well, this one was 4 and this one is 0.5. This one's more spread out, so maybe it's about 8. Right? I'm just making those values up. Okay. So I said that the area underneath the curve describes the likelihood that one random variable is selected and it falls within those parameters. So if we want to know what is the probability that one random value is selected from this distribution and it lands between, let's say, 9 and 11. What is the probability that one random value is selected and it lands between 9 and 11 in this distribution, which is a normal distribution with a mean of 3 and a standard deviation of 4? Well, okay, let's compare that to a different question over here. In this distribution, let's say I want to know what is the probability that one random variable is selected and it lands between 7.75 and 8. Okay, so I want to know that guy. Or separate from that, how about this one? Let's say I want to know what is the probability that it lands between 23 and 27. Okay. They look like separate questions, but they're connected in that they all have a space which is indexed by the same multiple of standard deviations away from the mean. If you notice, 1.5 sigmas, 1.5 times 4 is 6. So this first value is 1.5 sigmas away from the mean, whereas the second value is 2 sigmas away from the mean at 11. Whereas here, 1.5 would be 7.75, and 2 sigmas away from the mean would be 8. And same thing here, 1.5 standard deviations away from its mean equals to 23. And 2 times sigmas away from the mean would be 27. So in terms of multiples of the standard deviations, these 3 different questions are all related that way. Now, how do we find the answers? So we talked a little bit about the evolution of math and how they found these things. First of all, we had to come up with an equation that described that curve, and then we had to apply some calculus to find the areas underneath curves between those things. So just as an evolution of math, at at one point it was important, it was required that in order to find the probability that some x value in this distribution, that x is greater than 9 but less than 11, is equal to this ugly integral that goes from 9 to 11 of 1 over 2 pi, square root of 2 pi times 4 e to the negative x minus 3 squared all over 2 times 4 squared dx. That is a really ugly, nasty integral that gives you the answer, this blue part right there. Right? And then in this case, okay, that would be another ugly, nasty integral from 7.75 to 8 of 1 over 2 pi square root sigma of 0.5 e to the negative x minus 7 squared all over 2 times 0.5 squared dx. Nasty integral as well, very difficult, but that'll give us that little area right there in blue. And finally, we have this integral from 23 to 27 of 1 over 8 times 2 pi square rooted e to the negative x minus 11 squared all over 2 times 8 squared dx. It's really nasty, okay? But all of these answers turn out to give you the same result, okay? Because they have the same multiples of standard deviations away from their means. So, in the evolution of math, instead of having to solve it this way, some clever third person thought, well, why don't we just solve it for one of them, and then if you have a question about a different one, then you can refer back to the one we solved, and they put their answers in a nice table somewhere, okay? So they worked with one of them. So if you're going to work with one of them, why not pick some very nice, easy values? Instead of working with 11 and 8 and 7 and 0.5, why not work with mu equal to 0 and sigma equal to 1? It's a little bit kind of arbitrary that they chose those values, but at the same time they make a lot of sense because they make the whole thing just a little bit easier, okay? So we call that when we are centered at 0 and, mu equals to 0 and sigma equals to 1, then we call that the standard normal distribution. So let's erase this a little bit. So let's say we have, and I'm just making it big just to make sure it pops out for you guys. It's called the standard normal and for the standard normal distribution, mu equals to 0, sigma equals to 1, right? These guys go on forever that way, these guys go on forever that way. And what is the other thing we know about the variable that helps us identify that we're talking about the standard normal distribution? We no longer use the variable x, we use the variable z. Okay? The letter z is connected, is used for the standard normal distribution. Whenever you're talking about standard normal distribution, you're talking about the letter z as the random variable, and the mean is 0 and the standard deviation is 1. Okay? So now what we do, if we wanted to find these other answers over here, we'd have to think about, well, how many standard deviations away from the mean are each of those points? And we would find the z-score. That's what the z-score is asking about specifically. The z-score of a number, the z-score of 9, is how many standard deviations away from the mean is 9 in this distribution. So let's find the z-scores for 9. For x equals to 9, the z-score is going to be z-score equals to 9 minus its mean, which is equal to 3, divided by its standard deviation, which is equal to 4, which is going to be equal to 6 divided by 4, which is going to be equal to 1.5. Okay, so the z-score for 9 is 1.5. Now what's the z-score for 11? For 11, the z-score is going to be equal to 11 minus 3 divided by 4, the standard deviation, which will be equal to 8 over 4 or 2. Okay, so the z-score of 9 in this distribution is 1.5, 1.5 standard deviations away from its mean to the right, and the z-score of 11 is going to be 2 standard deviations to the right of the mean. Good. When we do the other ones, you'll find that if we did the z-score of 7.75, the z-score of 8, the z-score of 23, the z-score of 27, you'll find that we'll get the exact same results. This will be 1.5 standard deviations away from mean. This will be 2 standard deviations away from mean. Right? Look at the space here. This is from 7 to 8 is a 1, divided by 0.5 is 2. And from 11 to 27, this space is 16 divided by 8. We get a 2. So the z-score is going to be 2. So if we go over here to the standard normal distribution and we find 1.5 and 2, then we can get a region of the standard normal distribution which is proportionally equivalent to the others. So now if I find this answer, then I'll know the answer to the rest. Is everyone clear so far? No questions about the concept. I know I haven't really answered any questions directly, but we need to know these concepts before I just jump into what you punch in your calculator. Right? The real answers are really easy. You just punch a bunch of stuff in your calculator and you're done. But you got to understand what it is we're typing into our calculator to get those results. Okay, well again, back in the old days, okay, well then that means we'd have to do an ugly integral here, but it's not as bad as the rest. So this integral would end up being from 1.5 to 2 of 1 over 2 pi square root e to the negative x squared over 2. So a little bit nicer than the rest, but still pretty ugly. All right, so someone, some math person sat down in a dungeon somewhere and figured out this integral and many others, many integrals involving this, the standard normal distribution where mu is 0 and sigma is 1, and then he wrote all those answers in a table, right? So that's the standard normal distribution table for which your book pushes you to. So when you read the book, it'll talk about standard normal distribution tables all the time. And how they find an answer to this question, for example, is that they find the z-score of 7.75, the z-score of 8. Then they go, okay, go to the table and find the area trapped between 1.5 and 2 by using the tables, right? If you're going to do that, remember that the way the table works is that it gives you the area to the left of a particular z value. So you wouldn't be able to find this answer directly. You're going to find the area to the left of a z-value of 1.50, and then find the area to the left of 2.00, and then you subtract those two, and you're able to get the particular slice we're interested in. Good? Questions? Okay, but we're not doing that in this class. We don't do tables. I need you to know that, how to use the table, or what it means, because that's what the book is going to push you to, as well as when you do your homework and you hit the help me solve this. It directs you to that, and if you don't know what that means, then you get confused. But okay, so no questions about the z-tables and all that? We were okay with that before, right? Okay, so now how are we really going to solve it? Well, we get to use calculators. So we're going to use 2 functions in this chapter of our calculator that will help us solve these. The first function is normal CDF. So calculator functions. So first of all, let's say, for example, that I have a normal distribution like this. Normal, and let's say that the mean is, I don't know, I'm just making something up here. How about 7, and sigma is 3. And I want to know what is the area trapped between 9 and 13. I want to know that space right there. Okay. So for us, we're going to say that the probability, what random variable should I use here? Can I put a z? Is that okay? Can I put z there? Or I should say, what's wrong with putting z there? Why can't I put a z there? Because this is not a standard normal distribution. Z is only used for standard normal distribution, center at 0, sigma of 1. This is just some random distribution, so we have to use the letter x. Okay, so the probability that one random variable is selected, x, and it is trapped between 9 and 13. Some random variable is selected and it lands between 9 and 13. Well, that's going to be equal to normal CDF lower limit, which is going to be 9, upper limit, which is 13, with a mean of 7 and a standard deviation of 3. Good. Questions, comments, issues, No? All right, let's try typing it into our calculator. Practice. So that means that this area right in there has got an area of 22.97%. Any questions? Any questions? No? Okay, so it's normal CEF, lower limit, upper limit, mean, and standard deviation. Okay, notation. Sometimes they ask you to find something that looks like this. So note that C sub alpha means find the value such that this is alpha. That area up there. So this is Z sub alpha right here. Okay. So if they ask you, for example, find Z sub 0.37. Just making up a random number there. That could be the question. Find Z sub 0.37. Okay, so that means that we have, well, what's the mean and the standard deviation going to be in this question? It's got to be 0, 1 because we're using Z. Z is always connected to the standard normal distribution. So mean mu equals to 0, standard deviation equals to 1. This is the standard normal distribution. And they're asking me about this. I want to find Z sub 0.37, which is the Z value that traps the top 37%. That's what that means. Okay, so this is kind of like the reverse of that question. Over here, we are given values along the horizontal axis. We are told a segment of the horizontal axis, and we want to know what is the likelihood that one random variable lands inside that segment. Okay. Now, on the other hand, over here, we are given an area. We have this area in red given to us. It's 37%. This area right there is 37%. And I want to find the Z value that traps the top 37%. Good? Okay, so to do that, we have a nice calculator function that will help us figure that out. It's called inverse norm. So the way inverse norm, so given area A, given area A, so this is capital A right in there, then the value of x such that the area to the left, so that's where it's a little confusing. This notation represents the area to the right, whereas our calculator works with area to the left. So given area A, the area to the left of some value x in some distribution where the mean and sigma are given. Now, they don't have to be the standard normal distribution. They could be anything. But in particular, if you're talking about the standard normal distribution, then mu is 0 and sigma is 1. So given some normal distribution, you do have to know that it's normal, with a given mean value and a given sigma value, if you want to find the value of x that traps the lowest area A, then x, the number that does that for you is in norm, capital A, the area to the left, comma, mu, comma, sigma. That's what we have to know. Okay, so this is the calculator function that will help us. So going back to this question, we wanted to know this. What is the number that traps the top 37%? Well, that's the same thing as asking you what's the number that traps the lowest what? This is the top 37%, and the white negative space over here is 63%. I want the number that traps the lowest, 63%. Remember, we need to know that because our calculator only works with areas to the left. So then z sub 0.37 is going to be equal to in norm of 0.63. Make sure you put it as a decimal. Don't type in the 63 there. Comma 0, comma 1. Because we're talking about the standard normal distribution z. But like I said, this function will work with any normal distribution, not just the standard normal distribution. Any questions about that? Okay, so let's find it. I'm getting 3319. So what does that mean? How do we interpret 0.3319? Is that 33%? No, this is the value along the horizontal axis. We were given an area. We're looking for the horizontal axis value, the z value, which traps the top 37%. So this is indicating for us that if we have standard normal distribution with mu equal to 0, sigma equal to 1, right? It's centered right at 0. Then the number, the value that traps the lowest 63% is going to be 0.3319. That'll be the number that separates the lowest 63% from the top 37%. Any questions?